Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is complex numbers expressed using polar format. Our objective is to introduce complex numbers using polar format and learn to mathematically manipulate complex numbers using polar format. This lecture is predicated on the assumption the viewer has watched the complex numbers rectangular format lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. If you recall in the aforementioned lecture, we learned to express a complex number using rectangular format as a pair of coordinates, a real horizontal x component plus or minus an imaginary vertical y component times j. Additionally, we learned that the acts of addition and subtraction of complex numbers using rectangular format essentially boils down to keeping the real with the real and the imaginary with the imaginary, a task even a snowboarder has a realistic chance of not messing up too badly. While functional and well-suited for addition and subtraction of complex numbers, in my personal opinion, rectangular format doesn't really convey the true nature of a complex number and is somewhat unwieldy when performing multiplication and division. An alternative means of expressing complex numbers, polar format, dispenses with the multidimensional aspects and gets straight to the point, namely a magnitude pointed in a specific direction. A complex number expressed in polar format includes a magnitude, z, acting at a specific angle, theta. Angular position is measured in units of degrees, using the right side of the horizontal axis as the origin. Positive angles up to 180 degrees are rotation in a counterclockwise direction. Negative angles up to negative 180 degrees are rotation in a clockwise direction. This means complex numbers expressed using polar format with angles between 0 and positive 90 degrees places us in the first quadrant. Those with angles between positive 90 degrees and positive 180 degrees places us in the second quadrant. Those with angles between 0 and negative 90 degrees place us in the fourth quadrant. And finally, those with angles between negative 90 degrees and negative 180 degrees place us in the third quadrant. We'll examine means of converting between rectangular and polar format and vice versa in later lectures. Today's lecture will limit ourselves to just the act of multiplying and dividing complex numbers, a task especially well suited for polar format. To multiply a pair of complex numbers expressed using polar format, one multiplies the magnitudes and then adds the angles. To divide a pair of complex numbers expressed using polar format, one divides the magnitudes and subtracts the angles. 2. Easy. Consider complex number A with a magnitude of 7.9 at an angle of positive 60.5 degrees, and complex number B with a magnitude of 10.5 at an angle of positive 27.3 degrees. A is in the first quadrant, as is B. If we're being asked to perform the operation A times B, we multiply 7.9 times 10.5 and add 60.5 plus 27.3 degrees to obtain the result 83 at an angle of 87.8 degrees. If we're asked to perform the operation A divided by B, we'll divide 7.9 by 10.5 and subtract 27.3 degrees from 60.5 degrees to obtain the result 0.7524 at an angle of 33.2 degrees. Note I've taken the trouble to redraw the results of A times B and A divided by B using different graphs. This is not only necessary because the acts of multiplication and division shift the scale of the result, this also implies that the act of multiplication and division of complex numbers yield complex numbers with wholly different properties. This step isn't absolutely necessary for today's lecture. However, when we apply these techniques to electrical phenomenon, I find this additional step helps individuals conceptualize the results they obtain. As an example of what I'm trying to convey is the expectation that voltage times current, two different yet related properties, yields power, a wholly different property altogether. I like to think of electrical properties using three different yet related domains. The first being impedance, a property roughly equivalent to resistance, the second domain being shared by voltage and current, and the third and final domain exclusively for power. Like I said, this will make more sense in later lectures. For now, let's just deal with the numerical results of multiplication and division. Let's try a couple more illustrated examples of multiplication and division using complex numbers expressed in polar format. Consider complex number A with a magnitude of 9.9 at an angle of 83 degrees. Complex number A is still inside the first quadrant. Complex number B has a magnitude of 8.9 at an angle of negative 40.9 degrees. Complex number B is inside the fourth quadrant. When we multiply A times B, we multiply the magnitudes and add the angles taking into account the sign, to obtain the result of 88.1 at an angle of positive 42.1 degrees. If we're asked to perform the operation A divided by B, we divide the magnitudes and subtract the angles taking into account the sign, to obtain the value of 1.1 at an angle of 123.9 degrees. Again, note the results of multiplication and division necessitate the use of different scales because of the size of the resultant magnitude.